So we have a program here that's going to be based on dynamics of the atmosphere, ocean, and how these connect to climate scale processes. So I'm Jim Thomas, and I'll be giving a very basic lecture on geophysical fluid dynamics, the basics of fluid flow in the atmosphere and the ocean. So we'll start by defining GFD. So geophysical fluid dynamics, in a broad sense, it refers to fluid dynamics and geoscience as a real intersection. So in that sense, it's very broad. It applies to not just flows in the atmosphere and the ocean, but also to magma, lava, all these flows in the Earth's interior, and even planetary flows and so on. So when you look at Earth systems, we have the atmosphere and the ocean, and they're coupled. And in addition, we have different modes of precipitation. We have radiation, incoming solar radiation coming in that heats up the atmosphere. We have biosphere interacting with atmosphere, and we have all this Earth surface and all these living beings that are part here. We have sea ice and their effects on long-term climate changes and so on. So it's a very complex system, and to describe this and model this, we need to understand very different processes and how they couple. So we'll see some of these processes during this week. But geophysical fluid dynamics, primarily, we're going to focus on flows strictly in the atmosphere and the ocean, and some of the basic features in this talk. So here's a movie that's showing us the flow in the atmosphere. So we're looking at really the motion of clouds here. So the planet, this is really from NASA, and they're showing the flow in the atmosphere, and the planet has been cut open in a way that you can see this rectangular region. You see these eddy-like structures or vortices. We'll see a lot of this in this talk. These vortices evolve and transfer tracers and gases in the atmosphere, and they flow over the atmosphere, flow over the continents and the oceans. So this is an example of large-scale flow in the atmosphere, and this is a typical flow in the ocean. This is again from NASA Jet Propulsion Lab, and we're looking at the surface speed of the world's ocean. So this is from a global simulation where the equations of fluid dynamics is being integrated, and we're looking at the surface speed here. So you see these vortices or jet streams. So they're similar to what we saw in the atmosphere. You have these large-scale currents in the ocean, which breaks up into these vortices or eddies, as they're called. And near these continental regions, you can see these fast fluctuations. So these are tides. So near the continental regions, tidal conversion happens, and you end up generating a lot of tides. And as we'll wait for this, these continents to move, you can see near the continental shelves again fast fluctuations. So these fast fluctuations refers to tides primarily, and other kinds of waves that are excited when winds blow. So again, here you see these major current and eddies or vortices spinning off them. And when we look here, you can see this blowing effect on the sea surface. So this is atmospheric wind forcing the ocean. So atmospheric winds excites a lot of waves in the upper ocean. So that's being shown here. And here you can see again a lot of these eddies and vortices. They are interacting with these fast fluctuations. So this is how the ocean looks. And the previous movie we saw the atmosphere. So the atmosphere and the ocean at its core is really an interaction of a lot of these slowly evolving vortices or eddies and fast fluctuating waves. So now we'll take a look at the equations, relevant equations here. Now, when you apply Newton's second law, so this is how you derive the equations of motion. So people learn this in a fluid dynamics course. The first course in fluid dynamics will teach you this. When you think of fluid dynamics and fluid motion, you apply Newton's second law to a fluid parcel, and F equal to ma takes this form. So the right-hand side of this equation are all the forces. So we have pressure force, this is the gravitational force, and we have viscous force. And on the left-hand side, we have acceleration of the fluid. So this is the mass times acceleration term. Here I have normalized by mass, so this is really the acceleration, and this is the force per unit mass. And this is called the incompressibility condition, which states that the flow density changes are negligible. So these equations are what I call the incompressible Navier-Stokes equations. So here, velocity is a vector which captures the velocity components in x, y, and z direction. P is the pressure, rho is the density. Nu is what's called the kinematic viscosity, and we have the Laplacian gradient operators here. So this is the very famous Navier-Stokes equation, which applies to fluids flow. And this is typically useful at order meter, order 10 meter scales, smaller scales. But when you think of flows in the atmosphere and the ocean, the rotation of the planet and density changes in the vertical direction matters a lot. So if you think about it, we are on this rotating planet and we are in a rotating frame. So now we have to change our coordinates from an inertial frame to a rotating frame. So this is something you learn in a physics class. So if you are an inertial frame, you can go to rotating frame by adding this Coriolis term. So this is the Coriolis term, which constitutes the Coriolis force. So if you have a position vector r in the inertial frame, you can convert the derivative of that position vector, which corresponds to velocity in the inertial frame. You can write it as the velocity in the rotating frame plus this term. And we need acceleration, so you differentiate this again, and that leads to this term. So this is the Coriolis term effect in the Navier-Stokes equation. So this is a new term that comes in because we are in a rotating frame and we are on a rotating planet. So this is how you modify the equation to take into account the effect of rotation. So here omega refers to the rotation rate of the planet, and we are in this rotating coordinate frame now. Phi here refers to the gravitational potential. So the previous slide I had this g term. This is the acceleration due to gravity, but this works if you are on a plane and acceleration due to gravity acts vertically downwards. So that's why we have this negative g z cap. But if you are on the sphere, you need to express gravitational force as a potential. Gravitational force being a conservative force, you can write it as a gradient of a potential. So phi is a gravitational potential, and these equations are in coordinate invariant form or coordinate independent form. So any coordinate frame you can apply this. So if you can apply it on a sphere, or if you are on a spheroid, or if you are on the Cartesian grid, you can apply these. You just have to replace. You just have to write gradient, Laplacian, all these terms in the corresponding coordinate form. So that gives you the equation in whichever frame you want. And now the viscous term, this last term here, this matters at really small scale. So when you think of flows in the atmosphere and the ocean, so for everything that follow, we're thinking of scales of the order of 10 kilometer, 100 kilometer, and 1,000 kilometer scale. So at these scales, the viscous term has a very little role because the viscous term, this term acts primarily at order centimeter scale. So for large scale dynamics in the atmosphere and the ocean, it's common to ignore this viscous term. And so hereafter we'll ignore this term. So we have what are called the inviscid fluid equations that applies to large scale dynamics in the atmosphere and the ocean. So these are some useful approximations when you're interested in local flow dynamics. So if you are on so if you say you're interested in capturing the dynamics in the Indian Ocean or the Bay of Bengal or North Atlantic regions or the Pacific. So if you're interested in local regions, what you do is you make what is called a tangent plane approximation. So you fit a plane on the latitude that you're interested in, and we're interested in capturing the dynamics in the neighborhood of this region. So you write the Coriolis term. So in the previous slide, I had 2 omega. This 2 omega, I can project this on a local plane. So that's being done here. You put a tangent plane and you can project the rotation rate on the plane, normal to the plane. So that's this component. So F refers to the projection of the rotation of the planet, the rotation vector, onto the normal of this plane. And so if the angles are not marked here, but you could imagine an angle theta, which corresponds to latitude. So you write the rotation vector F as F times Z cap, where this is the Z cap now is the unit normal acting on that plane. And so you can write this rotation rate as 2 omega sine theta, where theta is the angle it makes with the vertical, which corresponds to latitude. And then there are two things you could do. You could say, I'm interested in a constant latitude. So in that case, you would fix theta to a particular angle, theta naught. So if you stop here, this is called the F-plane approximation. So in the F-plane approximation, what you do is you treat the rotation rate as a constant given by, which depends on the latitude. You could do better by saying, I want to capture dynamics in the neighborhood of this region. So then you do a Taylor expansion of this expression about a latitude theta naught. So you capture the constant and the leading order linear term. So this is a leading order linear term. And this term, with some work, you can write it as a constant beta times y, because y is this coordinate acting along the latitude and coordinate. So you can write the rotation rate F as F naught plus beta y. So if you ignore this term and if you say I'm interested in this constant angle, this is the F-plane approximation. If you retain the beta, the first order Taylor series expansion, this is called the beta plane approximation. And both these are used in different models. If you're interested in strictly local dynamics and you are interested only in certain kind of waves, you would go for the F-plane approximation. But if you want to capture the dynamics in the neighborhood along some latitudinal variation, you would put in the beta plane approximation. This can capture new kinds of waves that we'll see later in this day. So that's the F and beta plane approximation. Now we'll look at dominant balance. So if you looked at the movies that I showed earlier, we saw a lot of these eddies and vortices. And when you look at data from the atmosphere and the ocean, we see a lot of balances that doesn't really involve the flow to leading order. So a popular one is what's called the hydrostatic balance. So hydrostatic balance is marked in red here, which again, I think many of you would have learned this in schools and colleges. So the idea is you have the vertical gradient of pressure balancing the gravitational force. So this is a full equation that we saw earlier. And if we focus on this red part and look at the vertical balance, to a leading order, you find in the atmosphere and the ocean that pressure gradient in the vertical direction matches the gravitational force. So this is the dominant balance, and the flow appears as a weak perturbation sometimes. So this breaks down when you have strongly convective events in the atmosphere. You have cloud-related processes, strong precipitation. These things can change hydrostatic balance, but as long as you're far away from these strong convective events and so on, to a good approximation, hydrostatic balance works and holds in the atmosphere and the ocean at large enough scale. So 10 kilometer and above, you find the hydrostatic balance acting very often. The other dominant balance you see in the atmosphere and the ocean is called geostrophic balance. So this is a dynamic balance because it involves the velocity field. So here I marked the balance. It's the Coriolis force term balancing pressure gradient. So F cross V is the Coriolis term, and this is the pressure gradient, but now in the horizontal direction. So if you balance these in the horizontal direction, you can take this expression and you can, so if I take a cross product of this with F, after some manipulation, I can write the velocity as this constant times F cross gradient P. And if you write out this expression, so again, from vector calculus, you would remember that gradient P acts in the direction of increasing or decreasing pressure. So the maximum rate of change of pressure is given by gradient P. So when you say F cross grad P, this is now tangential to the maximum rate of change, or it acts along constant pressure lines. So this is telling us there's a flow that's in geostrophic balance acts along constant pressure surfaces, or isobars as I call it. So this is a very important balance in the atmosphere and the ocean, and you see this very often in weather maps and ocean circulation maps when you look at them. So here's an example weather map. This is plotting contours of constant pressure. So pressure equal to constant lines or isobars are plotted here. And when you look at the flow is along these isobars in these large scale atmosphere and the ocean. So this is a feature of geostrophic balance, and this is again very particular to rotating stratified flows like atmosphere and the ocean. So those of you who have seen fluid dynamics at smaller scales, so if you think of pipe flows, for example, in a pipe, you need pressure gradient to drive the flow. So you use a pump or a motor to generate a pressure gradient, and the pressure gradient is what drives the flow forward in pipe flows. Whereas as you see in the atmosphere and the ocean, it's really the opposite. Pressure flow is not along pressure gradient, but it's tangential and along isobars. So that's a feature of this dominant geostrophic balance that we persistently see in the atmosphere and the ocean. Now, if we combine geostrophic and hydrostatic balance, we get what is called thermal wind balance. This is again another a very important balance condition in the atmosphere and the ocean. So from the equations, in the horizontal direction, we saw geostrophic balance. So the Coriolis term balances horizontal pressure gradient. And in the vertical, we have hydrostatic balance. So pressure gradient in the vertical direction balances the gravitational term. We could differentiate this expression with respect to Z. So if I differentiate this with respect to Z, I have a vertical derivative of velocity getting in here. And when I differentiate pressure with respect to Z, I can substitute this expression, rho times G. Now, rho density can change in the horizontal direction. And so when I plug it in here, I get this. So this balance is called thermal wind balance. And we'll see why this is called thermal wind balance in a second. So this is telling us that the vertical derivative of the horizontal velocity can be balanced by horizontal gradients in density. So now if you, so we have equations for density and pressure and so on. If you use what's called an equation of state, you can relate density changes to changes in temperature. So in any fluid in general, density change corresponds to some change in temperature. So I could replace this density with some change in temperature. So I can write this gradient rho in terms of gradient T or temperature. So this, and then this becomes a remarkable expression that tells us that I can have a horizontal gradient of temperature, and that can be balanced by vertical gradient of a horizontal flow. So this is a very striking thing, and this wouldn't happen in a non-rotating fluid. So if you had a non-rotating fluid, so imagine you had hot coffee, and the hot coffee, as it cools, you might get a temperature gradient in the vertical direction. So you might find that the upper part of your coffee is cold, and below you might find it, sorry, upper part might be hot, lower part might be cold. So you can have a vertical gradient in temperature often, but you can't maintain a horizontal gradient in temperature because it will collapse and it will go back to a stable configuration. But when you have a rotating fluid, you can have this balance where a horizontal velocity with shear, vertical derivatives are often called shear, the shear can balance horizontal gradients in temperature. So this is a laboratory experiment that can be set up if you have a rotating tank. It's a very popular experiment for people when they teach geophysical fluid dynamics for undergraduate students and high school students. This is a picture from this book, Marshall and Plumby's first course geophysical dynamics book. We are looking at a concentric cylinder. So you can actually put in ice in a cylinder, and the fluid surrounding it is regular water. And this establishes a horizontal temperature gradient. Inside we have this cold, and around this outside we have warm fluid, and that sets up a horizontal temperature gradient and therefore a horizontal density gradient. And if you start rotating this, you'll set up a flow, a horizontal flow with a vertical shear with the structure in the z direction. So this is an illustration that is shown with this rotating setup. So you put dye in this rotating fluid, it will shear and develop a balanced condition where horizontal gradient in temperature is balanced by this vertical shear. So I think I have a movie to show this. So this is from an experiment that was done at University of Washington, Seattle. And so it's the same setup. We have ice in the inner cylinder, and in the outside cylinder we have regular water. And he's going to introduce some dye here. So this dye being introduced, and so if you had a non-rotating fluid, this dye would just diffuse. But with a rotating fluid, it can develop this sheared structure. So this is a horizontal velocity field that's in balance with this horizontal temperature gradient. So this is thermal wind balance, and this is very important when we think about flows in the atmosphere, because the poles are cold and the equator is hot. So there's a gradient in temperature from pole to equator, and that can be balanced by horizontal winds in the atmosphere that have a vertical structure. So this thermal wind balance is very important for large scale flows in the atmosphere. You also see this at various scales in the ocean. Okay, so now we'll look at two popular models that can be used for simulating flows in the atmosphere and the ocean. So the first one is what I call rotating shallow water equation. Now, if you look into numbers that correspond to atmosphere and the ocean, the horizontal scales for the large scale flow is of the order of 100 to 1,000 kilometers. So in the ocean, the large scales can be order 100 kilometers. In the atmosphere, it can be order 1,000 kilometers. When you look at the vertical scales, they're much smaller. So the ocean depths are typically 5 kilometers and below. The atmospheric height, if you include troposphere, stratosphere, and all this, it's order 10 kilometers or less. So this helps in modeling it as a shallow fluid where the height divided by the horizontal length, this is a small parameter. So this is what's called a shallow fluid approximation. And the shallow water equations capture a thin layer of fluid whose height is much smaller than the length, and it has constant density. So this is an approximation where you assume you have a fluid of constant density, that is rotating. So that's so you could go back to the previous equations that I showed you, and you could do what is called a perturbation analysis or perturbation approximation using this as a small parameter, and you can derive these equations. You can also start from first principles, mass and momentum conservation, and you can get to these equations. So here we have equations for the evolution of velocity. So V here is the horizontal velocity vector. U and V correspond to velocity in x and y direction. We have a height field. So we have a mean height, uppercase h, and we have fluctuations with respect to that mean, which is denoted by little h. So we have an evolution equation for h. So the mass conservation equation that I showed you earlier changes into this equation for height. And this is a closed system that tells us how the velocity of this fluid and the height of this fluid changes with time. And this fluid has constant density. So now in the atmosphere and the ocean, density changes a lot in the vertical direction. So if you want to model density variable fluids, what you do is you put on multiple layers of shallow water stacked on top of each other. So this is a very common modeling strategy used in the atmosphere and the ocean community. Especially many popular ocean models are multi-layer shallow water equations, where you assume you have, let's say, a fluid of density 1 unit, and above this you would put in a fluid of density 0.9, and above that maybe density 0.8, and so on. So by having many layers of shallow water stacked above each other, what I call multi-layer shallow water equations can model many of the complex features that I've seen before with constant density layers that are rotating. So that's the shallow water approximation. The second model that's again popular is called the Boussinesq system of equations. So the Boussinesq appears when, especially in the ocean context, density changes in the ocean are really small. So it allows us really to write the density as a constant part plus a small perturbation, where the small perturbation delta rho it's small compared to this leading order part rho naught. So we have a constant plus a small perturbation for the density, and you can write the pressure as a leading order part, which depends only on z. So P naught is in hydrostatic balance. So this should be P naught. P naught is in hydrostatic balance with rho naught. So these guys are in hydrostatic balance, and then we have a perturbation delta P, which is again small compared to this leading order part. So if you use this as assumption and put this in these equations that we looked at earlier, and we define a scaled pressure as delta P divided by P naught, you can define buoyancy. So buoyancy is really a negative acceleration due to gravity times. So this is delta rho. So this is delta rho here divided by rho naught. So this is the buoyancy variable. So if density is it really comes with negative sign of buoyancy. And if you recast this into the equations, we get left hand side remain the same, right hand side has now gradient P. Because we have scale pressure, the density scaling has been absorbed here, so there's no more 1 over rho appearing here. So it's gradient P, except that this is now scale pressure, and the buoyancy variable appears here in the vertical direction. So the acceleration due to gravity term with density multiplied, we have recast into this buoyancy term in the equations of motion. And now buoyancy is this variable, and it's conserved along fluid parcel. So we have an evolution equation for buoyancy, and in the absence of any source or sink, this buoyancy is just advected by fluid parcels by the fluid velocity. So that's the equation for buoyancy. And again, we have incompressibility equation, which tells us that the divergence of velocity is 0. So these are the Boussinesq equations. And now we can do one more simplification to the Boussinesq equation, which is again popular. So if you write the buoyancy expression that we had before, if you write buoyancy as a part that depends only on z, the vertical direction, and a small perturbation, you can write that. So when I differentiate this with respect to z, and I define dv by dc, vertical rate of change of buoyancy, this dv by dc, I'm writing it as n squared. So if you have a stably stratified atmosphere of the ocean, so stable stratification means the density decreases as you go up. So if the density decreases as you go up, buoyancy appears with negative g delta rho. When I differentiate this with respect to z in a stably stratified configuration, it will be positive. So this dB by dc is what's called n squared. N is called the Brunt-Vaisala frequency or the buoyancy frequency. And the physical way to think about this is if you have a again, a stably stratified atmosphere of the ocean configuration. So imagine you have two vertical layers. We have Z naught and Z naught plus zeta. You take a fluid parcel that has a certain density, rho, and you push this fluid parcel to a higher level, higher vertical location. And when you push this here, now the surrounding fluid has density less than this particular fluid parcel, because density is decreasing in the vertical direction. Density here is less than density here. So when I push this fluid parcel here, the density of this parcel now is higher than the surrounding fluid parcels. It gets pushed down by gravity or the buoyancy force. And the similar way, if you push this parcel down, because this guy has, this is lighter than fluid parcels here, it gets pushed up. So you can show with some calculation that if you move these parcels up and down, it will execute a simple harmonic motion given by this, where n is the frequency of these oscillations. So that's why this is called the buoyancy frequency. And in general, it can depend on z. So n can vary with vertical direction, because n really comes from vertical derivative of this buoyancy, which depends on density. So if you assume density is linearly varying, which is a good approximation locally, as in some places in the oceans, if you assume n is constant, sorry, if you assume density varies linearly with vertical direction, then you get n as a constant. Otherwise, in general, n can depend on z, which means the frequency of the oscillations also depends on the vertical location. So that's the buoyancy frequency. So that brings us to a very popular way of writing the Boussinesq equation. So these Boussinesq equations are written out here. So we have the Coriolis term, which comes in due to rotation, and this is the term that comes in due to stratification. And notice that in this Boussinesq system of equations, we have two implicit time scales in the system. One is given by this rotation rate. The inverse of this corresponds to the local rotation rate. And the n, which corresponds to the time scale associated with density stratification. So we have two time scales associated with these equations, but it doesn't have any explicit length scales that appear in the equation, which is a very interesting feature of Boussinesq equation. So you have two time scales given for you from these equations, but no explicit length scales. So those are the Boussinesq equations. And now we'll look at important non-dimensional parameters that tells us decide which parameter regimes we are in the atmosphere and the ocean. So if you look at the Boussinesq, as I said, there are two time scales, n and f, but there are no explicit scales. So if you introduce a scale, if you say, I'm interested in dynamics that happen at the order of, say, h, which is the depth of the ocean or height of the atmosphere, if you put in a vertical scale, now I can use this to generate a horizontal scale. So LD is the deformation scale. So this deformation scale, so if you put in numbers here, n over f is typically order 100 or so, close to 100 n over f. And then h, if you put in numbers, you get that the deformation scale in the atmosphere is order 1,000 kilometers, and deformation scale in the ocean is about 100 kilometers. So these are this deformation scale is a very energetic scale in the atmosphere and the ocean. So a lot of those eddies that we saw in the first couple of movies, the vortices that we saw, they have scales of the order of deformation scale. So in the ocean, for example, instabilities are generated at these scales. And so if you remember that ocean movie, we saw those major currents, and those currents were spinning off eddies, vortices. The vortices and eddies spin off at those scales which correspond to deformation scale, order 100 kilometers or 50 kilometers. So that's one parameter that's very important in the atmosphere and the ocean, the deformation scale. Two other parameters, one is called the Rossby number. So Rossby number, it's really an estimate for the strength of rotation rate of the fluid. So it's defined as U over FL. This is, you can think of it as a ratio of two time scales. U over L, U is, if you use order meter per second and L you put in meters, U over L gives you an estimate for the time scale of the flow evolution. And when I divide that by F, it's ratio of the fluid time scale, fluid flow eddy evolution time scale to rotation rate. And Rossby number will be small when you have a fluid that's very strongly rotating. So when F is very large, given other quantity is fixed, we have small Rossby number or strongly rotating fluid. And when you have stratification, you can define what is called Fruit number. So Fruit number is, this is one way of writing Fruit number. That can also be thought of as a ratio of two time scales. So U over H is some estimate for the vertical eddy turnover time scale. and n is the buoyancy frequency that we saw earlier. So this number gives us a hint on the strength of the stratification. So strongly stratified fluids will have Froude number small. So we have these two parameters, and at deformation scale, again, if you put in numbers for the atmosphere and the ocean, you find that at deformation scale, for the large scale flow in the atmosphere and the ocean, both Rossby and Froude number are small. So these are two small parameters, and we can exploit these small parameters to derive approximate models that work for capturing complex phenomena in the atmosphere and the ocean in these regimes, small Rossby and Froude number regime. Okay, so now here's a slide on a difficulty with numerical simulation. So the equation we saw, if you think about the scales we have to resolve, the smaller scale in the system in the atmosphere and the ocean is order of centimeter scale. This is a scale at which viscous dissipation happens. So all the energy that we put into the atmosphere and the ocean gets dissipated at these scales. Whereas the larger scales, this is of the order of radius of the planet, so about 1,000 kilometers. So if you put in the numbers, you can actually see there are about 8 decades of spatial scales that are spread across, and that needs to be resolved. 8 decades are very hard to resolve in a numerical simulation. In people who work with numerical simulations with supercomputers, now you can resolve safely. You can resolve about 3 decades, and if you push, you can go up to 4 decades. But resolving 8 decades is really, really hard. And to make the problem more complex, there are a lot of time scales here. When you look at the fastest waves in the system, the fastest waves are time scale of the order of minutes. And how long is your long time scale? This really depends on how long you want to predict. So if you think of weather prediction that act over days, weeks, or months, long-term predictions, you are looking at order months. So there are about 6 decades of time scales from minutes to months. So 6 is already large, but if you're interested in climate change, we're thinking of decades or centuries. You put in the numbers, there are 9 decades in time scales that go from minutes to century. So this is again very hard to do with even the best supercomputers we have. So here is a realistic computation you can do. Now, if you put in grid, so this is again when you work with numerical simulations, the equations that we solved before were partial differential equations which are nonlinear. So you can discretize the planet, and you put in points, and at each point you can represent the partial differential equation by a discrete system by using finite difference, finite volume, or some spectral approximation. So that gives you equations on a grid, and this is a reasonable computation you can do now. 1,000 grid points in the horizontal direction or latitude and longitude, 1,000 grid points, and in the vertical 200 vertical level. So this is sort of doable with a supercomputer now. For short-term simulations, you could run days or week at this resolution, this spatial resolution, resolving fine time scale. But you can see this is just 1,000. So we are far from resolving 8 decades, and this would resolve. This still wouldn't resolve even 6 decades. It would resolve 4 or 5 decades of time scales. So we're very far from resolving all the time scales and spatial scales required for this problem. And this is just coming in from discretizing the PD and simulating. So when you think about climate change and all, we're still talking only about the fluid equations. You had to bring in other equations for radiation, convective dynamics, and a lot of other processes in the Earth system that we saw in the first picture. So a lot of things, once you represent that, it becomes really hard to simulate everything with the fluid equations, which is what makes long-term predictions in this community really, really hard. So now, what can you do if you're interested in just large-scale dynamics of the atmosphere and the ocean? So in the previous slide, we saw the Rossby and Froude number. Now, again, for scales that are large in the atmosphere and the ocean, if you're interested in 100 or 1,000 kilometer scales, we can apply an approximation, which is called quasi-geostrophic approximation. So here, the way this approximation works, we have rotation and stratification in the system. So at large scales of the order of 100 kilometers and larger, the Rossby number and Froude number in the atmosphere and the ocean, they're comparable and they're small. So epsilon is a small parameter which represents Rossby and Froude number, and this is small. So if you scale the equations, you can show that the equations take this form where I have an epsilon, the small parameter, multiplying all these nonlinear terms. And so when you look at the leading balance, so leading order, I can ignore these small terms. If I ignore these terms, at leading order, I get geostrophic balance. So it's a Coriolis term balancing pressure gradient. That's the horizontal balance at leading order. In the vertical, I have a hydrostatic balance. So I have the vertical derivative of this term, balancing buoyancy. So that's the vertical balance. And at leading order, when I look at this equation, at leading order, if I set epsilon to 0, I have W equal to 0. So at leading order, I have no vertical velocity. Horizontal velocities are in geostrophic balance. And in the vertical, I have hydrostatic balance. And now I can define what is called a stream function to write the velocity as the horizontal derivatives of a stream function. So this geostrophic balance can be used to write this expression, but I can write the velocity as the rotated gradient of a function psi. And then you can carry out again an asymptotic analysis where epsilon is a small parameter. And this gives us what is called the cosine geostrophic equation. So QG equation, it was a very useful breakthrough in this community around the 1950s, because as you can see, we have reduced all these nonlinear partial differential equations into a single partial differential equation. Here I have velocity. So I have three components of velocity here in the x, y, and z direction. So I have three time evolution equations here. And I have one time evolution equation. So you have four time evolving PDEs here. And I've been able to reduce it to a single time evolving PDE. And this is the cosine geostrophic equation. Q here is what is called the potential vorticity. And it's related to the stream function psi we wrote down here by this expression. So rotation, stratification appears in the equation. And the way you evolve is if I have an initial condition for psi or q, I can time step this equation. So once I time step and I get q, I can invert this expression and get psi. And once I get psi, I can plug it in here and I can write the velocity in terms of psi. So I have the velocity and I can time evolve this further. So this cosine geostrophic equation captures the evolution of the balance component of the flow. So if you think of the Boussinesq equations, we have a lot of dynamics in the Boussinesq equation. This equation captures dynamics of the balance component alone, the geostrophic and hydrostatic balance component. The time evolution of that can be approximated by this equation in the limit of rapid rotation and strong stratification. So Rossby and fruit number are small. So that's the QG equation. And so if you look into the literature on cosine geostrophic theory, some of you might have heard of the name Richardson. Richardson was a very famous fluid dynamicist who back in the 1920s tried to predict weather. So this was the first known attempt to predict weather. So Richardson was aware of the fluid equations, the Navier-Stokes equations, and the effect of rotation and all were known. So he tried discretizing a planet. So he designed, just like we saw that numerical grid in the previous slide, Richardson designed this spherical grid with 120 points in the latitude direction, 100 points in the longitudinal direction, and just 5 points in the vertical direction. So this is what we would call a very coarse grid, numerical grid. And he put this in and he tried integrating this equation. Now this is way before computers. So he tried to integrate this equation with pen and papers. So he didn't unfortunately succeed because this calculation that he used with the equations, he used a time step that was larger than was required. So in people who work in numerical simulations know this. You have a permissible time step for integrating equations, which is set by what is called a CFL condition. So if your time step is larger than what is allowed by the CFL condition, your simulation will just blow up. So Richardson's simulation blew up, but then he explained all the procedure that he went through and all his thought in a book, which was written based on this his failed attempt. And we have some turbulence talks coming up there. We'll see this quote. This is a very famous quote in turbulence. It refers to what is called the energy cascade in turbulence. So we have big worlds which have little worlds that feed onto viscosity. So this is a quote that tells you how energy flows in a turbulent flow across many different scales. And this quote appeared for the first time in this book, which is written based on Richardson's failed attempt at first weather prediction. And so after many years after this attempt, Charney was a meteorologist who used to be at Princeton, and Charney recognizes, this is a famous paper written by Charney in 1948, where he derives this cosine geostrophic equation. So Charney makes this point in this paper that the equations of motion are very complicated because we have a lot of dynamics, and somehow we have to focus on the dynamics that matter the most. And he makes the case that the balance component of the flow exploring everything else. Let's focus on the balance component of flow and derive a simpler equation for the balance component alone. So that is the Cauchy-Geostrophic equation. So we derived the Cauchy-Geostrophic equation in this paper. And this was a year later. This equation was also independently derived by Russian mathematician Obukhov. So many might have heard of Kolmogorov. So Kolmogorov was a very famous mathematician. Obukhov was one of the students of Kolmogorov. He derived this equation 1 year later. And the Cauchy-Geostrophic equation, the QG equation, is also called the Charny-Obukhov equation, based on the people who derived it. And so Charny derived this, and around this time, this was a time when the first computer was available. ENIAC, many of you might have heard this name. ENIAC was the first computer, and von Neumann was at Princeton at this time, IIS Princeton, and he had access to ENIAC, and he was looking for things that could be tried out with this computer. He wanted equations that could be solved with this computer, and Roseby, we saw Roseby number earlier. Roseby introduced Charny to von Neumann, and they collaborated, and on this computer for the first time they integrated the Cauchy-Geostrophic and simpler versions of that equation, and these were the first successful computer weather forecast. So the first computer weather forecast used the Cauchy-Geostrophic equation, and it kind of revolutionized the field, because with very limited computing power, it was almost impossible to integrate the full equations, but the Cauchy-Geostrophic model, which ignores a lot of fast dynamics, could be integrated with very little effort, relatively very little effort on the first computer. So that's all about balanced dynamics. So now we'll have one slide on internal gravity waves. So we saw the Boussinesq equations earlier. Now if you drop all the nonlinear terms, and if you focus on the linear equations around, so these are now the linear Boussinesq equations, where all the nonlinear terms are dropped out. And if you look for solutions in the form of waves, so you assume velocity, for example, depends on a Fourier amplitude multiplying e to the power I k rho x minus omega t. So this is something that represents a propagating wave. So if you look for waves, you can show that the frequencies here depend on the wave number by a relationship written out here. This is called a dispersion relationship. So dispersion relationship tells you how the frequencies of waves are related to the horizontal and vertical wave number. So kz is a vertical wave number, kh is a horizontal wave number, and with some work you can show that this expression has frequencies going from f, which is proportional rotation rate, and n, which corresponds to buoyancy frequency. So we have a spectrum of waves which are called internal gravity waves in the atmosphere and the ocean that spans this range. So here is a movie that's showing us waves and eddies in a small part of the ocean near the coast. In this movie, you see these fast fluctuations. These correspond to internal gravity waves. So these are, in this particular region, they correspond to tides. And you saw similar structures in the second movie that I showed. So we have these fast fluctuations which corresponds to internal gravity waves. And in the background, you can see these slowly evolving balanced flow. This is the geostrophic and hydrostatic balanced flow, which forms eddies in the ocean. And you have similar things going in the atmosphere. So in the interest of time, I've skipped the atmospheric movie, but the atmospheric flow looks similar. There are these fast propagating waves, dispersive waves, and these slowly evolving eddies or vortices. So this is a summary of what happens in the atmosphere and the ocean. You typically have this balanced flow that's in geostrophic and hydrostatic balance. This is a slow field that evolves on time scales of weeks to month, and this is in balance. And we have internal gravity waves that evolve on time scale of minutes to day, given by this dispersion relation. So if you look for signals in the ocean, for example, so this is the Fourier transform of a time series in the ocean. So the x-axis here is frequency, and the y-axis is energy contained in that frequency band. You see at the low frequency end here, this is where the geostrophic balance component lives, and all these are waves. So the fast high frequency component, these are all different kinds of waves. So this is these are wind generated waves. This corresponds to a tidal peak, and then we have what is called internal wave continuum. So all these are waves, and the balance component lives here, and this is how the flow very roughly looks in the atmosphere and the ocean, and you can capture the balance dynamics approximately using Cauchy-Geostrophic equation. So that kind of summarizes this first talk. So flows in the atmosphere and the ocean, as we learned, a lot of spatio-temporal scales, which makes it very hard to resolve all these scales. The equations governing them are very complicated. They're nonlinear PDEs. We could track some of these features numerically, but you'll have to rely on the local computational resources you have. large-scale dynamics for the balance flow alone can be captured by the Cauchy geostrophic equation and its various simplifications. QG-like models, they don't capture the fast waves we saw in these movies, a lot of fast waves, which needs to be resolved for a lot of weather prediction, atmospheric mesoscale activities, and so on. So we have to somehow track waves in the present day, which these balance models can't do. And a lot of our numerical models are still far from solving all the relevant scales. So if you go by the rate at which computing power is growing, they say by 2100 or so, we'll get to a reasonable computing setup where we can resolve 7-8 spatial decades. So we're still far from resolving all the spatial scales. You can find more details in these references. I've taken most of the material from textbooks and videos from NASA JPL websites and all. So here's what we're going to do for the rest of the week. So we have this roadmap. So we have, so this is a very basic GFT lecture. We have 2 more GFT-like lectures going to be given by Manikantan and Kanabiran. They'll talk about waves and turbulence in the atmosphere and the ocean. And then we'll have Vishal, who is going to talk about atmospheric processes, convection, cloud, so on. He'll introduce moist dynamics, how moisture renders equations of motion. And then we have Suvarna, who's going to talk about Indian monsoon and some of its features. In the oceanographic direction, we have Bishak, who is going to talk about small-scale ocean processes and numerical modeling of them. We have Nadita, who's going to talk about the opposite, the large-scale ocean dynamics, climate-scale processes in the ocean and how to model them. And we have Anand Janadeshikan, who's going to give 4 elaborate lectures on large-scale features of the ocean circulation, and how the ocean dynamics connects to climate and how to couple them. So that's for the atmosphere and the ocean. And for climate, we have Ashwin, who's going to talk about simplified mathematical models. As we saw a lot in this talk, it's very useful if we can make simplifying approximations and get useful models out of these complex equations. So Ashwin will tell us how simple models can be derived and it can be used for climate scale processes. Anshuman will talk about the other extreme. He'll talk about developing climate models and using climate models to predict features and dynamics of climate. And then we have Manasa, who's going to talk about resolving wind speed, which is a very important feature, wind speed in climate model. How do you resolve that? And then we have a very dedicated series of lectures by Aman Gupta, who's going to talk about machine learning and its applications in GFT, atmosphere and the ocean. So Aman is somebody who is a GFTer who has been recently doing a lot of these machine learning problems. So he'll give a very hands-on intro with codes on how to use machine learning for many of these complex processes. So that's the end of this talk. So I'll leave you with a few tips. So this workshop was primarily put together for a lot of these young people who are not necessarily familiar with the atmosphere ocean community and the problems there. So this field has a lot of exciting problems that needs young, bright minds. So newcomers should take use of this opportunity, and we have a lot of breaks between talks. Try to meet people and get into conversations and see how much you can grab from these people here. We have a poster session, with 2 poster sessions on Thursday and Friday. So all the student participants try to present a poster. We still have a few days for that, so you can still make a poster and put it there. So please present a poster. And for the machine learning lectures, make sure you come with a laptop. This is your opportunity to learn machine learning stuff hands-on from first principles. So Aman is going to sit with us and teach us how to code these things. So come with a laptop and make sure you install Python and Jupyter Notebook on your laptop for Aman's lectures. So I'll stop there, and we have some time for questions before we break. Yeah, I think there is a... Can you pass the microphone?
Can you go to your previous slide?
Previous slide, yeah.
Yeah, previous to that also.
Which slide is this?
No, one more slide. Yeah, no. Next slide. Yeah. So why is the slope minus 2.32?
Why is, say it again, why is?
Why is that slope at the...
the slope, these things can vary a lot. It depends on where you look. This is like a best linear fit. Depending on where you look in the ocean, it can change.
So is it something to do with the ratio of how much energy going upscale and downscale?
At this location, yeah. I mean, the spectrum, this is a power spectrum. So you can roughly compute the energy at these scales. And the slope is a reflection of how low the energies and waves are compared to the eddy field. Yeah.
Okay.
Yeah.
So the previous slide.
This one.
So what are the colors there? And the temperature.
So this is a question. So this is really let me just change this chat. So this is showing us the surface speed, and I think light color is the fastest, and as you go to darker blue, it gets slower.
So when we were deriving the equations in the very starting first two slides,
Right.
when you converted from the inertial to the non-inertial frame,
Yes.
there should also be a centrifugal force. How is that taken care
Oh,
of?
there is. Yeah. So that's a very important detail that was skipped. The centrifugal term can be absorbed. You can write it as a gradient of a potential. So that gets absorbed in the pressure gradient.
Okay, so in all these videos that you showed in the first two slides and this one,
Yeah.
so what are the time scales that are being used? At what time?
For the movies, you mean?
Yeah, for the video. Initially, also you showed the first two slides.
Yeah. So the whole thing is order year, and the dynamics we see. So in the atmosphere, dynamics happen over order days to weeks.
So
And
these are on daily basis.
The movie. I mean, the frame rates are controlled to show daily rates.
Okay.
But they're obviously sped up. They speed it up to so that we can see it in real time.
Okay. For the rotating shallow water equation, so is it similar to the Kelvin-Helmholtz instability that is responsible for the turbulence?
Well, rotating shallow water is a system of equations. Within that system, you can have many instabilities. But Kelvin-Helmholtz instability as it is a different thing. It's an instability, whereas the rotating shallow water equations is a system of equations.
Because can you just go to the slide?
Which slide was this? The shallow water, yeah.
This one. No, next one, this one. Because
yeah,
the similar diagram I have seen the Kelvin-Helmholtz instability, in which this particular stage was the initial stage. And with time, the rotation and the water state increases, and it ends up into a turbulence on the atmosphere.
Yes, yeah. So, I mean, yeah, the diagrams, they might look different, but they mean different things. So here, we're looking at this thin layer of fluid, and these equations correspond to this thin layer. In Kelvin-Helmholtz, you can have you have an interface, and you can have two fluids with different densities and different properties, and you're disturbing the interface, and you're asking how does the interface evolve. So that's instability. Whereas this is a set of PDs, nonlinear PDs that capture dynamics of this interface. So within this interface and within this equation, you can have many instabilities.
So it is possible that they are somewhat related.
Again, Kelvin-Helmholtz is an instability which you can capture similar things with this model, but they're not the same.
Okay, last one. Sorry. For the challenges part that you've written, the challenge is the numerical simulation.
Yes.
Just can go to the slide.
Let's see.
Yeah, this one.
This one.
Yeah. So for the numerical grid, there are 1,000 into 1,000 to 200.
Right.
But don't you think there will be a problem at the polar region?
There will be, yeah. Pole is a big problem. You'll have to do things to map this and make this a non-singularity. Usually the pole can be a singularity.
So is there any work going on related to this?
There's a lot of work. So probably in the climate modeling talks, Anshuman might talk about this.
Okay, so I'll ask him. Thank you.
Okay, yeah.
Hello. Yeah, in all the equations, are we not just like we ignored viscosity, are we ignoring thermal conduction also?
Right, yeah, viscosity was ignored because we're thinking of scales that are very large, order 100 kilometers and above. But when you go to small scales, you would need viscosity.
No, about thermal conduction.
Yeah, convection is also not covered here. Radiation, convection, they're all things that should be put in. Moisture, these are complex things that we'll see in following talks. Okay, so yeah, maybe it's a good time to break. Okay, one more.
So in the slide about the fast fluctuating waves, especially in Patagonia, I did notice that it's more prominent in the eastern side of the continent. So what exactly triggers it in one side and it's not very prominent in the western side?
Well, so tides are generated by a complex process when these, because of moon's force, it excites what is called barotropic tide. And the barotropic tide gets converted across what are called sea mounds in the ocean. So there is mountains in the ocean where tides crash, and that generates these fast waves. So if you have a lot of sea mounds here, that will generate more tides. And so
It's
it's really
influenced by the topography
yes,
of the ocean floor.
yes, that's what controls it. Yeah, maybe last one more question and we'll break for coffee. Yeah, last question. Or there's the last. Maybe two questions. Oh, chat. Okay. So let's see the chat. First question is, how can we include electromagnetic processes such as lightning in the geostrophic model? Well, that's really an open question because geostrophic model is very simple, and it's not designed to capture lightning-like processes. And the second question is, what exactly do you mean by decades in spatial scale? Okay, so decade is, the largest scales that we looked at is 1,000 kilometer. The next scale is 100 kilometer. So that's a decade. Going from 1,000 to 100, that's a decade. And when you go to centimeter scales, we have 8 decades there: 1,000, 100, 10, 1, and so on. So that's what we mean by decade. And yeah, last question, and then we'll break.
Yeah, you said about moon's gravitational force.
Yes.
Affecting the magnetic flow of the ocean.
Yes.
So how do you incorporate that gravitational force into the equation, the shallow water equation?
You add a gravitational potential. So you can go to the shallow water equation and you can put a forcing in terms of a gradient of a potential to keep track of.
That equation of the Earth or the both the forces?
The equation that I showed did not incorporate the tidal force. You'll have to put in separately. The equations I showed all the equations I showed were unforced, whereas all the simulations that I showed were forced. You have to force these systems to get a response. Okay, so we'll break there. And let's see, the next talk is at 11:45. So we have 15 minutes break, coffee break. So we'll meet here again in 15 minutes.